production data. Okay. I think I already installed all the packages. I think I did. No, doesn't matter. If I do it again, it doesn't matter. Okay. Now this is the electric production data. You can see you have data that starts in 1985, in January 1985, and then goes to February 1995, and so, okay? So we have frequency of 12, we have monthly data there. And the plot, it looks just like what you showed. If I do the fit AR, for this one, it gives me a lambda that is, could be 0, right? 0 is in this interval. And if I did the Box-Cox transformation, the other function, the Box-Cox lambda of the series, it gives me a value minus 0.19. She's very close to 0. So that's a clear indication we need to work with the logarithm, right? Now let's look at the ACF and the PACF of the natural log of the series. This is dying very, very slowly. That's a clear indication, and you could see the trend in the series. So it's a clear indication that you need to take one difference. Let's look at the ACF and PACF of the first difference. And that, what the sort of things that you need to notice here is that there is the ACF is dying very slowly. See, you have large spikes at 12, at 24, and so on. So it's dying very slowly. That's a clear indication you need a seasonal difference of order 12. Okay. Now, so far so good. So I take the seasonal difference. And I'm calling it D12, D1, because it's the seasonal difference of the first difference. It's a difference of the first difference, but lag 12. So with that, I take the seasonal difference of order 12. Now I look at the ACF, and now it seems clear that I should have a model that has, on the non-seasonal part, it has two significant lags here in the PACF. That is telling me that it's very likely an AR on the non-seasonal part, an AR at least 2, an autoregressive of order at least 2, because of these two spikes here. These are also significant, but again, the partial autocorrelation function is the one that gives me a hint on the order of the autoregressive polynomial. Okay. Then when you look at what's going on here, it lags 12 and 24. It looks also, look at what happens at lag 12 in the PACF. At lag 12 in the PACF, you also have a significant lag at lag 12 and lag 24. So this is telling me also that I may have on the seasonal part, on the seasonal component, I must have two autoregressive terms. Okay, two autoregressive terms and one difference, and I'm working with the difference of order 12 of the first difference. So the natural model to try would be this one, which is the SARIMA with the log of the electric production, and it's an AR2 with one difference on the non-seasonal part, AR2 with one difference in the seasonal part. Okay, so it shows this problem with the p-values. Now, let's look a little bit more in detail here. These p-values are very small. So we may try to fix this, right? We may try to fix this thing and see if we can get an improvement here. What the sort of things can we do? Well, what we can do is analyze the residuals and feed a model to the residuals. Okay. So this is the ACF of the residuals, but now what I'm doing here is looking at the structure of model one. I have the several components, and in the component called fit, I do have the residuals, right? So I'm going to call the receipt M1 because these are the residuals of model one. To the residuals that came out of that model. It's a time series of 397 elements. And now you look at the plot, which is I had seen before. It looks okay, except for there's some couple of places here where we have outliers. That it looks like very extreme observations. See, everything seems to be centered around. Let me get my hand around here, right? And have a few points that are going beyond those barriers that I just draw. So I could consider these things outliers. This could be generating the fact that we don't get a very good model. That's a possibility. And that's something to consider. There are procedures to try to, it's like you make it like if these were missing observations, and then you forecast them, replace them in the data to see how the model changes. But what we're going to do now is a little bit different. I'm going to analyze the ACF of the residuals and the PACF of the residuals. Now these are now my residuals, and you see the autocorrelation function of the residuals and the partial autocorrelation function of the residuals. Now, if remember that we at some point in the class we saw that if we could model the residuals, we could find a model for the residuals that where the remaining term was actually white noise. We could correct the original model using that model. Okay, so let's this it looks like for these residuals I could fit 0 differences because they're already centered around a constant value. Okay, and probably I will have 2 autoregressive terms and 2 moving average terms. And here in this side, if you see 1, 2, I have these 3 spikes are significant. Okay, so I may have something. Look at 12. 12, there's nothing going on here. 24, yeah, I do have a significant lag at 24. And I do have a significant autocorrelation at lag 36. So there's something still happening, and this behavior could be due to a moving average, seasonal moving average behavior, right? So we can try different models for the residuals, but if you try different models, this one looks good in a sense that almost all the p-values are above 0.05. Almost all of them are above 0.05, except for the first one. Okay, so in essence, let me show you something here. Let me share my. Let me stop sharing here. And stop sharing. And so in essence, what we did is we fit this model to the original series, but what we got as the residuals is not white noise. Okay, so this is the original model that we fit. But this alpha t, alpha sub t, is not white noise. Because the p-values for the Young box statistic were very small for all the period, for all lags. So one thing that can be done is we could model alpha sub t, which is what I just did in the script. So I could model the residuals and find a model, let's say phi prime b of b times capital phi prime of b alpha t. Now this becomes my series of interest, the residuals from the previous model, equals to theta prime b in capital theta prime of b times at, where at is white noise. Here at is white noise. Then from there, I can express alpha t as the AR polynomial to the inverse of the AR polynomial, the inverse of the moving average seasonal polynomial times the moving average non-seasonal polynomial and the moving average seasonal polynomial. And now I have AT here, which is white noise. Okay. So the full model would be this one. This will be the full model. This applied to ZT, so that's phi of b times capital phi of b applied to CT will be this whole thing. Okay, so of course the things get complicated because now I have, if I want to forecast, I need to work with the estimates of the model that we already have. So but that's a way that you can correct the model. That's a way that you can correct the model. Let me see if I can. So what do we do in cases like this? I mean, one alternative is what I just did, and work with the estimates of both models to do the forecast and all that sort of thing. Now, that's what in theory should be done. Now, in practice, let me go back to the original model. Yeah, I do have these p-values that are very small. But on the other hand, there's nothing of great concern in the ACF of the residuals. There's a clear pattern here, okay? There's a clear pattern. But some of this pattern may be due to those extreme observations that we're seeing, which are influencing the series to have some weird behavior in some places. So if forecasting is very critical here, then we could use the combination of the two models to do the forecast. Otherwise, we could try to evaluate how good is this model, even though it's not complying with all the assumptions of the model, how good it is in terms of forecasting. So I will split the data and leave the last, for example, the last 6 months out of the data set, and then predict those 6 months, compute then the mean square error for prediction, and if that mean square error was within reasonable values, let's say within a certain margin that's acceptable to whoever is the expert in this thing here, in electric power production, then we could live with that. We could live with that. Otherwise, the complication, because if you combine the two models, then forecasting is easy because you can. We haven't talked about forecasting yet. We'll talk about forecasting. It's just a matter of it's done recursively. But the problem then would be to compute confidence intervals for the forecasts, okay, prediction intervals. Then it gets very, very messy to get the confidence intervals for the predictions once we combine the two models. But there's a way to do it. So that's why I wanted you to look at this series. You can try different models. That there's not much improvement you can do over this one, over this model, but you can try to other models and see if one gives you better p-values here. Okay, but again, if this is the only thing that concerns me, this behavior, this curve, this behavior in the ACF of the residuals. This type of behavior is pointing out some autocorrelation. So we could try to fix it a different way. We could try to add 6-term autoregressive of order. Let's see, could be. And I have the graph for the residuals. Let's see. Here's the PACF and the ACF of the residuals. So I could try adding just autoregressive terms of order 3 or 4, but you cannot add only one term. You need to consider all of the terms. Okay, so for example, let me take this model that's the first one we fit, and I'm gonna change this thing. And I'm going to try to add other 2 autoregressive terms on the non-seasonal part, because this pattern is occurring not associated with the seasonal behavior of 12 months. And I could do the same. The p-values don't improve. Okay, so you still have this large spike. The pattern is not that strong. There's one very large value here of order 4. So I could try then to fix this thing running adding a moving average of order 4, which is it's too many parameters. Okay, it's too many parameters, and the thing will not improve. See, the p-values are still going to be very bad. Now, the advantage here is that this autocorrelation function is not showing any spike in the near, very close to the origin, let's say, that's significant, although there will be several parameters that are non-significant. If I say model 1, I have several parameters that are non-significant. See, the AR1 says it's not significant, but I cannot remove it because it doesn't work. The algorithm doesn't work like that. AR3 is not significant, and AR4, so it gives me back to the AR1. And you can iterate back and forth trying to improve the model, and you will not get very, very serious improvements. So we need to go with a practical approach and go with a model that's good enough to forecast what we need to forecast, and that's it. Okay, so there's as George Bock said, all models are wrong. All models are wrong, but some are useful. And what we want to do is we want to use a useful model, even though it's not perfect. Okay. Now, what you cannot do is, for example, in your final projects, just give up and say no. Yeah, you need to try to fix the model as much as possible, and have it comply with the assumptions as much as possible. Okay. Okay. Let's stop here, and I'll see you tomorrow at 10. Any questions so far? Comments, complaints?
No, we're good.
Okay, well, we'll see you tomorrow. Have fun.
See you tomorrow.
Thank you, teacher.
Thank you, teacher. Bye.
Bye.
Thank you.
Teacher. Bye.
Bye.